Hello everyone, and in this video we're going to now talk about what integrals mean because we just discovered them. So let's recall that in the last video we talked about how to get the exact area under a curve, and we'll call it, say, f of t. So if we have a curve, arbitrary curve f of t, and we wanted to find the exact area under the curve from a to b, the way we would do it is you would use Riemann sums. And the way you use rectangles to get the exact area, well, you would have to use infinitely many rectangles. But the way you approach infinities, because infinity is not a number, it's a concept, is we have to use limits. So what we said is to get this, we would do the limit as n approaches infinity of your Riemann sum, which is x equals 0 to n minus 1 for the number of rectangles, the width of each rectangle, times the height of every rectangle, like so. And that gets you the exact area in the curve. But in the last video, we talked about how we actually can write that using something in calculus called the integral from a to b of f of t dt here. So all this is saying is it's the area under the curve f of t on the interval a to b. Okay. So this video we're going to talk about is what is this saying, which really, this is all it's saying, but there's going to be different notations, and we're actually going to work on a problem that discovers how we can work with these rather than using this. Because again, the reason we don't use this is because it's lengthy, and a limit isn't actually a button because that's a concept. So we use this to apply that concept. So here we go. What the book will say is they'll say, okay, well, this notation from 0 to x of f of dtt is equal to, and they do, if you want to get, and what this is saying, before I go into what it equals, this is again saying the area under f of t on the interval 0 to x, okay? And now x can be any number, right? So if I did a picture of this to help you understand this, is so we have an arbitrary curve f of t, and we're just finding the area under the curve from 0 to, I know that's not 0. 0 should be over here. Make this more accurate. 0 to x. Well, the way we can get the area under the curve, in fact, is that instead of looking at this function f of t, we can look at its antiderivative function, and we would look at it at, well, we'll just say there's an antiderivative function f of x. Now, what this is saying is it just means that there's an antiderivative function in terms of x. And the reason it's in terms of x is because we don't know x is going to be. That gives us the area under the curve. That will give us the area under the curve from 0 to x on f of t. So the idea is that there's another function we can look at, the antiderivative function. So it's like we're working backwards that will tell us the area under the curve from 0 to that value on the function f of t. So, I mean, graphically what I'm saying is that we can represent this area as a different function, f of x. Well, if you evaluate it at, say, this value right here, if you find x, f of x, if you find this value right here, that's going to give you the same thing as the area under the curve from 0 to x. And that's what it's saying right there. And that's a very valuable thing because it's kind of like how with derivatives we talk about, you want to analyze a function's rate. Well, there's a whole new function to look at. It's derivative function or its slope function. Well, when we're taking the area under the curve, this sometimes can be seen as like an area function. While, again, with derivatives, it's a slope function. So you might still be lost. We're going to keep going and hopefully help explain this to you. All right. Now, a common mistake that I've seen a lot of people make is they say, Mr. Hein, why is it 0 to x f of t dt and f of x? And then what you end up thinking as a student who's learning calculus is you say, okay, I'm looking for patterns, and what I see is that you just take the antiderivative of the function f, we call f the antiderivative, and then you just plug in x. And I guess from a procedure standpoint, you're not wrong, but I just want to let you know that we could have written this as 0 to x of f of x dx, which is what I usually write, and that's what we usually write in math as a function with respect to its x. But this, it's not wrong to write this, it's just confusing. And that's why they use t and d of t, right? And why is that? So up here, we were looking at an area under f, or the area under the curve of f of t in the range of 0 to x, or you can think about it as the interval of integration was 0 for the function, for the values t between 0 and x, right? Because this was in terms of t. And that makes sense. If you apply that here, you're saying, okay, we're looking at the integration in the interval where x, the function x, has to be between 0 and x. And notice that it just gets confusing because this x and this x don't mean the same thing. This x is the inputs of this function, while this x represents the bound at which we're looking away. And that's why they don't like to use x and x, because they don't refer to the same thing, right? So if you, and then you'd say, you know, that's the antiderivative of f of x, or just to highlight, these two represent the same thing, not the x is there. And you can see it with the interval, when I write it as an interval of what we're integrating. It doesn't make sense. It's not wrong, just too confusing. And keep in mind, it doesn't have to be t's. You're more than happy to do, you know, f of y dy will equal the antiderivative function in terms of x there. That's fine too. All right, that's still saying to get the area under the curve of f of y on the interval 0 to x, we can find an antiderivative function in terms of x. Now don't forget, antiderivatives, note that there are infinitely many antiderivatives. So really what this is saying, and it's pretty amazing in a way, is that to get the area under a curve, there exists an antiderivative function that we can use to calculate it by just plugging it in. Okay. Now, how does this work with numbers? And let's clear this up. So what this is just saying right here is that if we want, it's just another way of saying it is if we want the area under a curve, we can look at its antiderivative function. All right. So I'm going to flip this paper over and let's look at an example. We're going to explore something together real quick that I don't think the book does necessarily a nice job doing. But let's look at 0 to x. Well, before we do that, 0 to x of f of d dt equals 3x plus 2. What does this mean? Let me just quickly talk about what this means with you. So what this is saying is it's saying this is the area under the curve f of t on the interval 0 to x. And when they say it equals 3x plus 2, what that is this is already the antiderivative of f of t in terms of x. And when I say in terms of x, again, it's because that's that bound. If that was a number, we would probably already have an answer there. But it's the antiderivative in terms of that bound that we're looking at, because that bound can change, right? Bound, as the bound changes, we need a function that accounts for that change. Right? So that's what that's saying here. But now let's get to the example where I'm going to explore. I got a little sidetracked. So what if we looked at the interval from a to x of, and let's pick an example of x plus 3, or don't use x again, because that's confusing when we have a bound of x. So let's do t plus 3 dt. Right. just to make sure we don't get confused with what x's we're talking about. So if I drew a graph of this, let's understand what this is saying. Is we have this curve t plus 3, which I could graph that. There's t plus 3. And I want to find the area under the curve from some value a to some value x. That's what this is saying here. Okay. Now, what I talked about on the front is that we know that there's an antiderivative function. So if we call this f of t, we know that there's an antiderivative function that we can get in terms of x. But there's more to it than that, and I'm going to explore that right here. So we just know that there exists, an antiderivative. Which, let's just keep going. We know how we can take the antiderivative of this. So a to the x of t plus 3 dt. Well, what's the antiderivative of t plus 3 dt? Remember, antiderivative is a function such that when you take the derivative, you get back the original function. And derivative, using the power rule, always subtracts 1. So the antiderivative, we would have to add 1. So it's going to be t squared, because if we took the derivative, it would go back to 1. And then the trick, if you haven't noticed it, is that once you add 1 here, then that is just what gets divided. So with derivatives, it multiplies the constant. With antiderivatives, it divides the constant. So then we're going to have 1 over 2, 1/2 t squared plus, and then that's going to give us 3t. And then we write this in terms of x. So that's going to give us 1/2 x squared plus 3x. But then the question is, what about the a? And let's explore that right now, and then we'll talk about it. Okay, so we don't even know if this is right, but we know that there's an antiderivative function. Let's find the area of this using geometry, because we can do that. So the area using geometry is going to be 1/2 base 1, which if I plug a into this would be a plus 3, plus base 2, which base 2 is if I plug x into that. So that's, sorry, actually it should all be in parentheses, plus base 2 times the height, and the height there is x minus a. Okay. Now doing some algebra, we would have 1/2. You would have ax minus a squared plus 3x minus 3a plus x squared minus xa plus 3x minus 3a. Simplifying this, we can see here that the ax and the minus xa will go away. And I believe that's it. So what we have here is, I'm going to put the x first. We're going to have x squared plus 3x. Oh, actually, that makes plus 6x. Because we can combine our x's. And then we have the a's, which is minus a squared. And then combining those, we have minus 6a. Okay. So again, this is the area under the curve from a to x. And now I'm going to distribute this, but I'm going to distribute in a certain way, where I'm going to say 1/2 x squared plus 6x plus, and then I'm actually going to take out a minus here, a negative from that, and do minus 1/2 a squared plus 6a. And if I write that one step farther, what we get here is 1/2 x squared plus 3x minus 1/2 a squared plus 3a. And this, again, is the area under the curve f of t, which was represented by t plus 3 on the interval a to x, two random bounds. Okay, well, x being a variable, so this being a constant and x being a variable. But what's fascinating about this is, if you look at when we took the antiderivative of f of t, we got 1/2 t squared plus 3t. Well, notice we have the 1/2 t squared plus t, but instead of t, they had x there. So this is the antiderivative as a function of x. And then we have over here 1/2, and there's the a squared, which is like the t, plus the 3a, which is like the t. So this is actually the antiderivative of a function as a. So that's fascinating because what we just discovered is that the integral from a to x, where a is a constant and x is a variable, but it could also be a constant, all right, technically, is of the function, and I'm going to go back and write f of t dt. What it's equal to is we take the antiderivative of that function, but we plug in its higher bound, x, and we subtract off the antiderivative of its lower bound. And that is very powerful because this is how we will calculate integrals. Now, big note, not every function has an antiderivative. Not every function has a closed antiderivative. What I mean by closed is it's not always possible for us to do. Sometimes you need technology to find it. Okay. Like we're not capable of finding it with the algebra and math skills we have currently available in the world. Okay. So let's see this in action and see how it works. Okay. So this again is accumulation of talking about how this notation 0 to x of this one right here, 0 to x of f of t dt, is that if you want to evaluate the area under the curve, well, there exists some antiderivative. And not only does there exist some antiderivative, but if you look at the antiderivative at the upper bound and subtract off the upper derivative, the antiderivative at the lower bound, we'll get the area under the curve. So again, that's the antiderivative at the upper bound minus the lower bound, the anti of the lower bound. Okay. So let's look at two examples, and you can see how this is so helpful for us. So say you want to find the integral of 1 to 2 of 5 dx. So just a constant 5, in which you probably know, okay, it's a rectangle with a 1, you know the answer is 5. But if we use what we know is the antiderivative of 5 is going to be 5x, okay? Because then if you take the derivative of 5x, you'll get 5. And then what we do is we evaluate it from 1 to 2. So this is a new notation, where sometimes instead of going straight there, we write f of x, or f of t, the antiderivative f of t, from a to x. And that's just the way they write that. So the antiderivative is 5x from 1 to 2. So then we say it's the upper bound minus the lower bound, which note, we get the same thing you're probably thinking, which is 5. Okay. Second example is, say you look at an antiderivative of 0, or the integral of 0 to pi halves of cosine of x dx, but the antiderivative of cosine x is sine of x. And we're going to evaluate that from 0 to pi halves. So then that does sine of pi halves minus sine of 0. Well, sine of pi halves is 1. Sine of 0 is 0. So this gives us 1. And that is how we use the integrals and antiderivatives working together. Now, graphically, if I wrap this up to help you see all this, originally, this problem right here was you have a curve 5, and you're evaluating from 1 to 2, in which we know that the area of that curve is, using pencil, 5. I don't know if you see that. Okay. But what we discovered is that we can look at its antiderivative, which is 5x. So the antiderivative function, or the area function, which is 5x. And if we just evaluate 5x at 2, so which was 10, and subtract off the area function at 5, well, 10 minus 5 also gave us that 5. And that's the idea, is that it's a whole new curve that we use to evaluate the area under the curve. It's a lot to take in. Definitely just think about it. You have to work through it. Ask me questions and just make sense of it all. All right. I'll be here if you need any help or need anything clarified. All right. Bye bye.